Hi, very glad to be here. So we actually run a workflow group that is kind of centered at Argonne and U of Chicago, and many of the team members are here, and we're going to try to do a lot of hands-on exercises as parts of the discussion. So I'd like to just introduce the people. Over here is Justin Wozniak and Tim Armstrong. In the back here, David Kelly and Yadu Nand. And Ketan Maheshwari may be joining us as well. I don't see him at the moment. Alrighty. So we're going to basically be kind of talking about workflow as yet another, and sometimes somewhat ignored topic of extreme scale and high performance computing. So I'll start with some overview and some definitions, and I'm going to spend the first part of this talk talking about generalities, just workflow, and then just mentioning briefly the vast number of tools that are addressing this style of application development. And then I'm going to focus on the workflow tools that our group focuses on, both as a research and as an application vehicle, and that's the Swift parallel scripting language. And then we're going to segue into hands-on exercises on both the original highly portable Swift version and then a new Swift version that's really tailored toward extreme scale systems and applications. Okay, so when we say workflow means a lot of things to different communities, but the central aspect of it that we're really focusing on here is that workflow is really what we used to call in the 70s programming in the large. In other words, it's the knitting together of applications from existing applications. In other words, building bigger capabilities or the ability to run scientific or engineering campaigns from large level piece parts. In other words, existing programs, very high level libraries, scripts for integration and things like that. So that's kind of what characterizes workflow, is that in ordinary programming, you're typically knitting together functions. When we talk about workflow, you're typically knitting together existing canned applications. So you may be doing this to make what's essentially a new application, in other words, a scripted manner of automating the execution of a large number of programs, or you may be doing it to basically execute your scientific or engineering work. You typically will be doing a campaign. Whenever you're using a very high-end machine, you're typically not running one application once. You're running a long chain of applications to pursue some investigation. And that process is what we call workflow. So it refers both to a means of getting work done within a domain, the notion of a flow of tasks, and it also refers to a high-level style of application development. So we often contrast it with scripting, and in some sense, really scripting, implementation of workflow is really one application of the class of programming languages that we call scripting languages. So I'd like to refer everyone to an excellent paper that came out somewhere around 1998 or so by John Osterhout about defining scripting as really the way to do higher level application construction, in this century. Two other terms that you'll hear a lot about are high throughput computing. So this was a term that was really popularized by the Condor team back in the 80s, and it refers to a style of workflow, and in a sense, the act of trying to get a large volume of computing done, typically over large periods of time. And when people talk about high throughput, they're really talking about delivery of cycles over time, often by the execution of large numbers of long-running application programs. Now, more recently, as workflow techniques started to sort of trickle down and be applied to a new class of extreme scale systems, we defined a term called many-task computing. And in some sense, it was an attempt to draw a contrast between high throughput computing, which really talks about a large but sometimes modest number of long-running jobs, and the new style of programming where we can take much finer grain applications, applications that only runs for minutes or even seconds or sub-seconds, on a very high performance platform and knit together millions or billions of these application invocations to either do a campaign or to form a new application. So many-task computing is kind of referring to the subdomain of workflow programming where we focus on smaller grain tasks, a lot more tasks, and the construction of real applications from these tasks, as opposed to high throughput of just getting a large amount of work done in a campaign. In the process of doing that, the community has really kind of reinvigorated this term data flow, which is a concept that keeps coming back in almost every generation, every decade of computing. Starting back in the 70s when the Lisp community was trying to figure out how to do things in parallel, how to start leveraging early machines, and how to get programming productivity out of that. And we'll talk a little bit more about data flow when we talk about the next generation of Swift scripting language. And then lastly, a couple of terms that are often, that you've probably been discussing in this workshop: data parallel versus task parallel. Workflow programming is typically task parallel, but we're starting to now see hybrid integrations where we have data parallel efforts running, or data parallel elements running within a task parallel program. And then lastly, single program multi-data is more typified, more typical of the MPI style of programming that has been a large focus of your work. Workflow kind of brings in sort of the term of multi-program multi-data, where the application, workflow style application will contain multiple applications within it, and there's a lot of asynchrony in part enabled by this notion of data flow programming. Okay, so I'm also going to try to, I've included a lot of material here. A lot of this I think you'll be interested in following up on some of these slides, but I'm going to zip through and skip many slides in the interest of trying to leave a little more time for hands-on use of some of these techniques. So this slide's a great illustration of a classic case of what we mean by workflow and a workflow style application. So this application is part of the one technique used in drug discovery. So if you have some modest number of complex proteins or biomolecules that are thought to play some role in a disease, and you've got hundreds of thousands or millions of molecule definitions of potential drug compounds that may have a beneficial or a negative interaction with these biomolecules, scientists want to do this massive search of applying docking techniques to ask, how does this molecule interact with this particular drug? So there's an application in this case called DOCK, which is like one of the many workhorse tools of the molecular dynamics and proteomics community. And these scientists wanted to basically run hundreds of thousands to millions of DOCK invocations. So this is a perfect example of workflow. N proteins times a large M number of molecules turns into an explosive number of application invocations. And the question is, how do we implement that on a variety of machines? On high-end machines, how do we deal with the I/O challenges, with the scheduling challenges? On distributed resources, how do we get data transport done? How do we bring tool to data? How do we leverage very disparate interfaces to different scheduling systems or different distributed cloud systems and things like that? So those are all the challenges of that kind of style of programming. And this style of programming really spreads through virtually every domain of science and engineering that we've encountered in over a decade of pursuing this problem. This slide illustrates many of the engagements that our team has done, and is very typical of work done by workflow communities throughout the world. For example, looking at simulation at a theoretical chemistry level of supercooled glass materials involves very deep nested parameter sweeps over molecular modeling tools. Protein folding may involve a lot of Monte Carlo simulated annealing to take a code base that is attempting to perform some kind of new algorithm for protein structure prediction and how a protein takes its shape, and then execute that hundreds of thousands or millions of times again in a variety of patterns controlled by deeply nested parameter sweeps. Okay? Climate modeling, in this domain, models running on supercomputers produce vast data sets, typically chunked up into files based on spatial regions or time divisions. And then after these models run, the community pores over the models with analytic tools that go through hundreds of thousands of large structured, typically netCDF files, and does diagnostics, does assessment of the model execution quality, starts to lift out some of the science hidden within that vast trove of data. So this again is a workflow driven not so much by parameter sweeps, but driven by the data structure of the data set and the tools that are being applied to do the diagnostics. And again, protein to RNA interaction is very much like our docking application. Subsurface modeling is a case where scientists need to do hybrid programming, taking large MPI programs and running those themselves as a workflow. And that's something also that we're getting very involved with as workflow meets HPC and extreme scale. And lastly, power grid applications. A large number of mathematical tools have to be explored in, again, sometimes in parameter sweeps, but also power grid modeling also takes on the nature of a big data problem where massive streams of data coming in from smart grid sensors are sort of now interacting with these models. And we need to both have ways to process big data and then correlate it with model execution, and in some cases with actually making decisions about grid operation. So the resources that scientists apply here are very vast and diverse, and they kind of range from the kinds of multi-core resources that are now pervading your desktop or your lab workstations, all the way through clusters of typically similarly multi-core nodes, supercomputing clusters such as Mira and Titan, and cloud resources. So these are really 4 or 5 classes, depending on how you look at things, of resources, each with their own kind of specialized programming models, each with their own interfaces. And what we try to do in the workflow world is look for ways to unite these things and to have an overarching high level, again, programming in the large paradigm to put these together. And so this environment and this sort of Tableau really raises a bunch of challenges. It raises the challenges of how do I transparently move data within my workflow? How do I sort of hide the difficulties involved in jumping between these systems? How do I generate tasks both at the rates needed to drive the scale of machines, but also how do I send tasks across very diverse interfaces? In other words, how can I find programming models that make it easy to sort of think in terms of the logical flow of your application and then map it to the complexities of this kind of environment? Okay, so this is sort of an example of the kind of things we're focusing on, where workflows running on central client nodes talk to a variety of machines, such as Cray supercomputers, campus grid structures that have campus resources united with domain-specific resources and workstation labs and things like that, all united in a seamless campus infrastructure, and then many campus computing clusters that you typically have access to. So we're many workflow systems address the problem of going sort of from where you are, taking your data from where it is and bringing it back and forth to these kinds of resources. Okay, so we've already talked about a lot of these patterns in terms of the applications. I mentioned, one of the things you encounter sometimes when you study workflow is this concept in the middle of this slide, the notion of data flow versus control flow. And as you study different workflow systems, you'll see that some express the structure of your application in terms of control flow, in other words, just specifying the order of task execution. Others sort of focus more on just linking your tasks together based on their data dependencies. And so the task-based expression of workflow typically leaves it to the programmer or user developer to specify the actual data transport, whereas a data flow-based system tries to automate that. Pipelining and concurrency is a big issue in workflow. In other words, how do we detect the opportunities for parallelism within the expression of a workflow graph? And you'll see that word come up over and over again in terms of workflow, because workflow application development is typically thought of as a dependency graph of running some set of things, then when those are done, collecting their output, analyzing them, passing on to the next stage. So this notion of a flow graph really pervades the field of workflow development and of workflow tools. And lastly, you'll sometimes see workflow combined in various interesting manners with other scripting techniques. So sometimes you'll see applications that do workflow inside the application, where the application is driven by a script written in a popular scripting language, be it Shell, Python, etc. And then those scripts will invoke workflow managers to do subsections of the highly parallel work inside the application. Other times you'll see the workflow manager at the top level driving ensembles or collections of other tools written in diverse languages. And so you'll very often see the pattern of a application written as a workflow program, then dropping down to sort of application-specific scripting, and then finally the application tools written in a programming language like C or Fortran. Okay, and then programming models is another field or subfield of study in the workflow area, trying to understand the diversity of the different models that exist for programming and trying to find ways to have an effective hybridization of these models to build seamless applications where within the overall application the right tools are used for the right level of things. So we often see workflow applications that link together MPI applications, OpenMP applications, and a wide variety of scripting languages. And we also see workflow capabilities coming out of our job schedulers. So most job schedulers today have some kind of elemental primitive mode for allowing job dependencies to be specified. So programmers that want to do very simple workflow programming can just write a script that emits control language for their job schedulers that specifies some amount of that flow graph that we talked about. Okay, so briefly, a set of tools that I'm just going to sort of walk through and briefly introduce some of the tools that are kind of popular in the field. High throughput computing, as I mentioned, was started by Condor, and I just briefly mentioned already this notion that schedulers have, some very primitive dependency tracking capability. Condor has a graph-specific workflow specification tool that's based on task dependencies called DAGMAN, or Directed Acyclic Graph Manager. So this basically has a very explicit task graph created by the user. The user creates Condor jobs as nodes of the graph. The nodes can have pre-processing and post-processing, and it's in those stages that the user typically has to explicitly put in their data management. And then DAGMAN itself runs as a job under Condor, sending jobs back into Condor, and from there out into cluster and sometimes into grid resources. So on top of DAGMAN, probably for more than a decade now, Pegasus has been making great strides in automating a lot of that data management the data management work. So Pegasus takes a flow graph also as an input and produces a Condor DAG as its emitted execution mechanism, but it automates a lot of the data movement, data placement, data location things, and it's been applied in a wide variety of applications. So you can go to the Pegasus site, for example, and see a very nice catalog of workflow patterns that have been implemented in across domains, and get a sense for sort of the diversity of those flow graphs. Now, several sort of parallel to the workflow world, kind of in part driven by the search for ways to program a cluster, to program cloud resources. Languages like Dryad and CL and Swift have emerged. Swift we'll talk about later because it's the language that we focus on and apply. Dryad came out of groups of Microsoft. I think CL, if I'm not mistaken, is out of Oxford, and they both have very data flow oriented notions in them. They're very programming language focused. So one of the differences you'll see between some of the programming tools and the workflow tools is that the workflow tools typically have more sophisticated embedded mechanisms to express the invocation of canned applications. Okay, so one of the interesting things we'll focus on in Swift is, how do we create a language where you're thinking in terms of data flow and programming, but the things that you're knitting together are themselves entire applications. So how do we make what sort of was sort of ad hoc scripting, how do we make that more structured? And that's a concept we'll come back to. And lastly, there's a few more things to mention here. You're all familiar with big data techniques and MapReduce and Hadoop. So those techniques are themselves a form of data flow processing, and you'll see the similarity between the notion of mapping a function to a set of data and then reducing the data. That triangular pattern is something that you see again and again in almost every workflow application, because it's like parallelize a lot of stuff, bring it together, repeat as needed, and then sometimes that pattern repeats due to an iterative algorithm. Sometimes that pattern repeats due to a complex algorithm that has many stages of processing to go from raw data or simulation down to final science or engineering results. Okay. Down at the low level, there's some evolving support, especially in this really nifty Swiss Army knife of scripting called GNU Parallel. And so Parallel is a way, typically a technique for running multi-core work. It has some limited support for more advanced cluster solutions, but it's really a way to say, I've got 250 cores on my lab workstation. How can I easily program to that? So it takes techniques that were sort of, prototyped over decades with things like Parallel Make, and it kind of more deeply embeds that into a shell. And I should mention there's another parallel shell effort that was done by Ed Walker, where he actually integrated a lot of these parallel concepts, including some of the MapReduce mechanisms, into Bash so that you could have those capabilities right in your shell. Okay, and then lastly, in the language area, I should mention that many languages, notably I guess MATLAB, Python as well, have a wide variety of tool support for doing workflow style programming within those languages. Okay, and those are typically language focused. Those techniques are really good at multi-core situations, really good at single cluster situations. They're not as well adapted as some of these other solutions that take more of a grid-based, multi-system, distributed system-based approach. And then a whole nother class of workflow is based on the idea of expressing a workflow by drawing it. So just as you would draw a flow graph in PowerPoint, a wide variety of tools like Galaxy or the Lani pipeline focusing on neuroscience applications, Taverna, Triana, Kepler. Microsoft had an effort on this that I'm not sure of the status of it, and it may have met limited success. A lot of these tools give you a visual way to stitch your workflow together, so you're kind of doing visual programming, and those tools tend to focus on sort of desktop interaction with a scientific pipeline, but not as much on the back-end execution of scaling that pipeline up. And now we're seeing a lot of efforts to bring those two worlds together. Have the ability to express a workflow either through a programmatic script or through a visual expression, and have a nice amount of interoperability between those two modes of representation. Okay. By the way, I should mention, please interrupt anytime you have a question. Be glad to stop and consider anything that's of interest. So one of the interesting things I want to start now shifting a little bit toward extreme scale. One of the things we talk about a lot is when you're faced with a given task, do you develop new code or do you try to reuse existing code? So, and then how flexibly can you integrate that code? So this slide and the next sort of illustrate this question with respect to BLAST. So the BLAST application is one of the most important popular tools in bioinformatics, and there's been a large number of diverse efforts to parallelize this. This experiment here kind of contrasts parallelizing BLAST as using a scripted approach. So David Mathog at Caltech wrote a shell script to do this kind of parallel BLAST, and then he wrote the necessary merging the reduction tools to merge parallel results. And then our group took that, expressed it as a Swift workflow, and did a fair amount of studying on it, including contrasting it with the same kind of parallel capability that was implemented using MPI as the workflow framework. Okay, and the finding on this was that the script is far more compact, easy to use, than to try to write an MPI program to achieve that kind of parallelization. Yet the scripted method really doesn't differ by more than 5 to 10% from the very meticulously coded, labor-intensive MPI way of doing that same task. This is kind of an interesting study in a paper cited, actually cited here on this next slide, that sort of compared some of these things with a focus on how does the data management problem get solved. Okay, so this brings us to sort of two fundamental problems in doing workflow and in scaling workflows to extreme systems. One is that as my tasks get, well, let me say it this way, to make the workflow technique, the high-level programming in the large approach effective, you have to be able to comfortably combine tools that have a wide variety of runtimes. And like I said earlier, anything from hours to hundreds of milliseconds as your task granularity. Okay, so hours, we're very comfortable scripting things that run for hours. We're not as comfortable using scripted techniques to put together things that run for milliseconds. And yet as we look at extreme scale machines, machines that have million plus cores, billion plus threads, the big challenge is how are we going to program those machines? And we believe that while some amount of work on those machines, maybe some large amount is going to be focused on massive capability applications, there's very similar applications in terms of their needs, their value, their importance, that have this many-task nature. And so we believe that workflow techniques play a major role and can play a major role in constructing those, again, taking the view of workflow techniques and data flow techniques as the outer level, expressing the outer level logic of those large applications, and then executing large combinations of other apps that are written in more tightly coupled techniques like MPI and PGAS languages and many core languages and things like that. And then the other, final note on that particular topic is that as the tasks get smaller, the task rate gets higher. So your data flow system, your workflow system has to be able to handle an increasing task rate and task dispatch rate to make that programming style feasible. So just do the simple math, if you had 60,000 cores at your disposal to run a many-task scripted application and your tasks are 1 minute in duration, you need an engine that can pump out 1,000 tasks per second to fully utilize that amount of compute resources. Okay, so if you look back historically, engines like Condor and Globus Task Dispatch were sitting there in the sort of maybe approaching 10 to low tens of tasks per second. Other workflow systems like early Swift started pushing out into the 500 tasks per second range. Experimental techniques like Falcon were pushing 3,000 tasks per second, but we're going to need millions of tasks per second to be able to really do data flow programming for large scale, capability class applications. And the similar argument similar challenge takes place at the data management level. So this task rate is also, since workflow applications are either coupled by exchanging files, or in more recent cases, exchanging in-memory packages of information, you know, more message-based. The file access rate or message exchange rate is also going up, you know, proportionally. So that includes both the data transport, you know, the data bandwidth, as well as the transactional rate of message or file exchange. So those are both, you know, big problems in scaling. So in terms, I've already mentioned some of the strides moving forward from the tens of tasks to the thousands of tasks per second, you know, across the task range and in the task problem. Similarly, let's see. So similarly, in the data side, I'm going to just point you to this study of looking at the data flow patterns of many task programming. This was led by Zhao Zhang at UChicago, and he's starting to characterize what we call the performance envelope, the data performance envelope of large-scale extreme systems. So as we program these systems, we see that there's a lot of challenges in moving data between apps and the file systems, effective use of local file systems, and really understanding what are the limitations of the file system in terms of what kinds of data we can move and how we have to shape that data to fit in the file system. So I'm going to just zip through this and show you sort of what I think is the key part here, which is this notion that a machine, a given large-scale machine or machine environment, has an envelope of capabilities in terms of the number of files per second that it can open, the number of blocks per second, and the size of those blocks that you can read off the file system, the differences between reading and writing and file creation and things like that. And that leads to sort of this multi-dimensional envelope expressed in this paper as a Kvyat chart. This particular slide is not extremely informative because it's lacking the scales. But the paper has a lot of information about, you know, this kind of study approach, and this is like one of the most relevant things to understanding the capabilities of doing workflow programming on extreme systems. And so the conclusion of this paper was to try to give the beginnings of a guide to workflow application developers for the nature of the machine envelopes and what kind of applications could be done, you know, on, you know, given the I/O constraints of a particular machine. And this work is, I think, you know, in a sense, at its infancy. This, as the machines change and evolve, this work is really important for being able to understand what we can do. Okay, so I'll leave that for reading. So, you know, a bunch of engineering and research challenges emerge from this. You know, in engineering, it's things like, you know, how do we integrate with the communication fabrics of the machine? How do we support interlanguage communication as we make workflow applications that use a wide variety of languages? Sort of on the research side, there's a lot of challenging scheduling issues, challenges of doing automated recovery, both challenges and opportunities, because workflow programs are typically expressed as graphs. The graphs give us a lot of knowledge in terms of the behavior of the program and help us deal with failures within the program. So because we have a graph, we can more readily reconstruct lost data if functional units of a large-scale machine go offline. That has the beginnings of techniques that we can use to recover data. Similarly, it has the techniques that we could use to plan the energy utilization or energy utilization trade-offs, because we're mapping a data flow graph onto physical resources. We can decide how many processing elements a given subset of that program gets. And then lastly, I'd like to point out another element that's going on in the community. This is work being done by Scott Kreider, who's actually in the workshop here at IIT, of trying to take this notion of many-task programming and drive it down as fine as we can to the point where we're exploring whether it's feasible to take accelerators, GPUs, and use their individual SIMD processing elements in parallel for diverse tasks to sort of bring, you know, many program techniques to a SIMD-based hardware device. Okay. Any questions so far on generalities? Okay. Let's see. So I'm trying to figure out how to both give you some of the background here and also get you started on some of the exercises. So I think hopefully on the agenda, you've got the links to the exercises for Swift. And so what I want to do now is basically introduce Swift to you because it's one of the things that we've been focusing on to try to address the problems that I've alluded to and the opportunities that I've sort of mentioned in terms of how we can structure code. So I'll talk real briefly about Swift, but you can almost get started on getting the tutorial downloaded while we're talking, and then we can sort of jump right into giving you some time to try things. And what I'm hoping is that within this remaining time, so I think we have about 45 minutes, I can cover a little more on the 2 generations of Swift, and then you could actually go to the 2 sections of your of the Swift handout. The first of which gives you sort of a very basic introduction to Swift, most of which is kind of desktop-like execution, and finally culminates in running some workflows on the Tukey analysis cluster. I'm not sure if you've been on Tukey so far this week, but you may have. And then I'd like to allow some time to also give you a taste of the new Swift Turbine, which is really addressing the challenges of extreme scale programming. So I'm going to try to accelerate just so you can actually have a chance to get started here while we have a bunch of people from the team that can help you through any problems or answer any questions. And then hopefully this evening, there's an abundant set of exercises here to take us into the evening. And now that we realize you have access to Titan, we actually may be able to give you some exercises that would let you try some of this stuff on Titan. Otherwise, we'll be running this mostly on Tukey and on Vesta. Okay? So Swift essentially is a scripting language, okay? And it's a scripting language specifically for the execution and integration of application programs. And it really does 3 things for you. Now, because it's a data flow-based model, it makes parallelism transparent. So our belief is that when you're programming at the high level of a very large application, you're knitting together very large building blocks. Those building blocks had a lot of meticulous attention paid to the scaling characteristics and the mapping to the machine of that particular code base. But when you're up at the high level doing what we call the outer loops of a big application, we believe you can afford to let the runtime systems and the languages do the parallelization for you. And that would lead us to a model where bigger and bigger machines are programmable with less and less specialized programming skills and knowledge, where you can take a function library and express it as data flow, and that's sort of the vision that Swift is driving to. So the second transparency it tries to give you is failure recovery, so the notion that it can automatically retry failing tasks and eventually, as we mentioned in a research problem, eventually recover large subgraphs of failing environments. And then the last thing it does transparently for you is it makes the location of where you're computing transparent. So what we're seeing with scientists more and more is that most scientists are confronted with a wide set of choices of where they can run their codes. They can run on campus clusters. They can get extra cycles from Amazon EC2. They can go out to Exceed or to the grids. They can come to a leadership class computing center or to Blue Waters. So scientists increasingly have this wide set of machines, and they have to solve the problems of coupling these machines together, of moving data between machines and things like that. So Swift tries to do that transparently for you as well. So it kind of runs in this environment where it sits on a client node, whether that could be a laptop, more typically it's a login host, and it can take data from servers like the local file systems, from grid FTP servers. It can go out over the network with HTTP and fetch data, and then has a variety of ways to move that data to a wide set of resources. Okay, so a basic Swift program looks like this, and it's basically looks a little bit C-like, is very functionally oriented. So in Swift, you basically encapsulate code as functions, and you write functions both to express your logic and to encapsulate the interfaces to external programs. So because it's data flow driven, every variable in a Swift program is write once, and this allows data flow to be implemented automatically. Every function call in a Swift program is conceptually parallel. So when you see a body of assignments, a block of assignment statements like this, these assignment statements are always executed in data flow order. Conceptually, they're all kicked off in parallel, and they block when variables that they need are not yet set. And that's sort of the notion of automatic data flow. Every variable is what we call a future, which has this kind of implicit data flow semantic built into it. So in Swift, you encapsulate programs. Let's see, I'm just going to jump over here. You encapsulate programs by writing application declarations, which give the program a functional header, and then acts as the interface to the command line invocation of that application. And you'll see this as you work through the exercises. And then, so for example, you would make an application called predict, and then now you can invoke predict as a function and write functional code around that, and that's how you specify your workflow. So in other words, this is basically workflow programming by doing ordinary functional programming. And then the workhorse, oops, oh, that's okay. The workhorse in Swift is this, this for each statement. So for each is a parallel loop. It says for each member of a collection or of a set of constants, do the loop body, and that's what basically achieves the large-scale parallelism in Swift. So we get kind of simple parallelism within a block, and that helps to expose pipelining, especially between parallel functions. But the for each statement really is the workhorse of the language. And that enables us to write nested, so I talked earlier about parameter sweeps or nested Monte Carlo simulation being one of the driving applications. So this is doing protein prediction in Swift with nested loops that, with a few simple loops, you can, invoke 100,000 tasks, some of which are embedded inside this internal function. And this application has been published in a few different papers that sort of walk you through the logic inside it. And then we can do, large graphs. So this is an example from neuroscience where a kind of ad hoc Swift script, shell script, was converted into Swift, and then that conversion essentially gave the user community kind of automatic parallelization of a large chain of neuroscience application invocations. And similarly was done in the climate space. Climate diagnostics were converted from very complicated C shell scripts into Swift scripts, and then this instantly gave a community that was sort of bottlenecked on analysis of big climate models a way to leverage cluster resources and distributed resources for doing large-scale diagnostics. So this for example, is this program, this flow graph expressed as a functional program where basically the top-level logic of that was expressed as a series of function invocations, many of these which are just wrapper functions to a C-coded application tool that's like one of the tool sets of this community. And then Swift also has ways to map data sets so that you can talk logically about your data on disk as if it's a set of structures and use that to have a very clean representation of your program. Okay, so I'm just going to very briefly, actually I'm going to take a little pause now and give you a chance to try the first set of Swift Swift exercises. Just in terms of a little bit of terminology, the first generation of Swift we sometimes call Swift K because it was built on top of the Java-based Karajan workflow engine. So it's it's this high-level language whose syntax you've just seen that in turn inside Java emits workflows in a lower-level workflow engine that implements all the futures and data dependency logic. Then a newer system, which I'll introduce to you in a moment, starts to now scale Swift up. and that's Swift-T, Swift Turbine, which now uses the turbine engine, and that's an engine that lets us break through some of the bottlenecks, and we'll talk about that in a moment. So I'm going to give you about 10 minutes now. I was hoping to do a little more, but why don't you spend 10 minutes giving the first set of Swift exercises a try, at least going through, I think, what's called the basics parts, I think 1 through 9, and see how far along those you can get in 10 minutes, and the rest will, you can pick up on that later. And then in 10 minutes, I'll give you a brief introduction to T. Maybe Justin will talk about it as well, and then you can try some exercises in Swift-T. So quick question?
The setup.sh doesn't seem to be doing what it should be doing. It doesn't put Swift. It's referring to things that don't exist.
Okay. Do one of you guys want to come and take a look at that, or is that everyone having that problem, or?
On Vesta, I had a problem on Tukey.
Oh, yeah. This can only run on Tukey. This has to run on Tukey. Sorry. Yeah, I think that may have gotten inserted at the front of the. If you have an old version of the web page, I think we inserted some words on that this morning, but it has to be run on Tukey. I think there'll be a segment of Swift T exercises on Vesta later. Justin, is the first Swift T is on Vesta? Okay, great. Okay. Any other questions while we get started in trying some of the stuff? Are you running it on Tukey, or?
Oh, we're supposed to run that.
Yeah, just to repeat that all of the part 1 and part 2 exercises, everything involving the ordinary Swift command has to run on Tukey only. So those exercises are. I think that release of Swift is not on Vesta at the moment. Who's gotten part 1 to work? Okay, good. So it's got some basic sanity. That's good to know.